All right, this lecture is for elastic potential energy. It says the time at our disposal each day is elastic. The passions we feel dilated. Those that inspire us shrink it, and the habit fills it. So you can see the dilation, the shrinking, that's involved in the elastic potential energy. So students should understand the factors that affect elastic potential energy with an emphasis on displacement in this case. You should be able to calculate elastic potential energy. You should also be able to relate elastic potential energy to work and power just like everything else. You should also be able to relate it to the law of conservation of energy. So, what you see here is the elastic potential energy is the potential energy that an object has due to its stretch or its temporary deformation. The most obvious example of that would be a spring. You can take a spring and you can stretch it out or you can compress it, and whenever you let go, it's trying to get back to its original position. It doesn't want to be deformed the way that it was. So what you see is you see the formula as written for the star chart, which is PE elastic is equal to 1/2 K x squared. This K term is a new term. Well, no, we talked about it with Hooke's law. It's the spring constant value. It's a measure of the stiffness of a spring. So if a spring is easy to compress, it has a very low value. If a spring is very difficult to stretch or compress, it has a very high value. The X term is the displacement of the spring, which we're going to talk about a little bit later, as far as because it's not just how long the spring is. Alright, this question asks us to sketch the graph of spring constant versus elastic energy. So when we do that, we look at the formula. We say PE elastic is equal to 1/2 K x squared. And we are looking specifically at the spring constant and potential energy elastic. So remember, every other term that we have is going to go away. So the 1/2 goes away and the x squared goes away because they're deemed to be held constant. So really what we have is PE elastic equals K, or Y equals X, or a graph that looks like this, where as the spring constant goes up, the potential energy goes up accordingly. Alright, this one says a spring is compressed, resulting in an energy of PE elastic. If the spring is compressed twice as far, what is the resulting elastic energy? So, what you should realize is that we are using the elastic energy equation. Squared. So, the K value is the same no matter what because we're talking about the same spring. Now, a lot of people get caught up on this because they say that the spring is compressed. In other words, it's squeezed together, so they think this X value actually goes down. But remember, this X value is just the displacement or the change in position. So really, if the spring starts here and is compressed to this term right here would be the X value. Okay? It would also be the same X value if it was stretched out to the same corresponding X. Okay? It doesn't actually make a difference whether it's stretched or compressed. This X value would be the same as long as it was the same corresponding value. So even though it's compressed, the X value is going to be larger. So what we can say is it is compressed twice as far. So what we can say is instead of X, we would have 2X. And remember, that whole thing is squared. Remember that displacement is a squared term. So as you double the displacement, what you actually do is you increase the total energy by a factor of 4. So we have 4 times as much elastic energy. This question says how much elastic potential energy is stored in a staple gun if it has a spring constant of 51 newtons per meter. At rest, the length is 0.115 and the length ends up at 0.150. So we initially have a spring that has a distance of 0.115. We then put some sort of force on it to stretch that spring to a distance of 0.150. So really, that gives us some information that we're going to need to calculate the amount of elastic potential that is stored. So really, we're looking for the potential energy that's elastic. We know the formula for potential energy elastic is equal to 1/2 K x squared. We have our K value, which is expressed in newtons per meter. So we have 51 newtons per meter. We also have our X value, although a lot of people will say, they'll try, well, which one's the X value? Remember, the X value is the change in length of the spring, or the change from the equilibrium position. So if it started at this length and ended at this length, what this X value actually represents would be 0.150 minus 0.115, or 0.035 meters. Alright, so now that we have our X value and our K value, we can solve for the potential energy. We can say PE is equal to 1/2 K X squared. So we go to our calculator and we say 0.5 times 51 times 0.035 squared. Oops. 0.5 times 51 times 0.035 squared. And we get a pretty small value. The amount of energy stored in the spring is about 0.0312 joules. So it's actually a pretty small value. This question says, what is the spring constant of a spring that stores 10 joules of work when compressed a distance of 10 centimeters? So in this one, we are trying to solve for the K value. We know that we have a spring that was originally some sort of length, and it has been compressed so that it is 10 centimeters shorter than it originally was. So since we know we're trying to solve for the spring constant value, we know that our formula is going to be PE equals 1/2 KX squared. Now, our PE value is an energy which is measured in joules, and we have 10 joules of work. Now we also have a distance of 10 centimeters. Now, we should know that we don't deal with centimeters by now, so that the X value should actually be 0.1 meters. Okay? If you're not sure how to do this conversion, go ahead and look it up online, or you can refer back to your notes from the beginning of the year. But you should know how to convert centimeters to meters by now. So now, PE, 10 equals 1/2 K 0.1 squared. So what we would do is we would divide, we can go ahead and do the math here. So we can say 0.5 times 0.1 squared. So you get 10 equals 0.005 K. Divide both sides by 0.005. And you get K is 2,000 newtons per meter. Okay, this question says a spring requires 10 joules to stretch 5 centimeters. So you have an original spring, you want to stretch it an additional 5 centimeters, so that this right here is 5 centimeters, and you say that that takes 10 joules of work. Okay, we want to know how much energy is required to stretch it an additional 12 centimeters. Okay, so what we want to do is we want to say, okay, I want to stretch it so that it's actually 12 centimeters further than it was in the second situation. So what you should realize is that the displacement from the original position is not 5 centimeters, it's not 12 centimeters, it's actually 17 centimeters. Okay? By now you should know that centimeters are not something that we deal with. But really that's the only piece of information that we have. So we're going to have to use this first situation that it gives us in order to figure out what the K value is. And so this is actually a two-step question. Ultimately, I want to know what the energy is. But in order to do that, first I'm going to have to solve for what the K value is. So what I'm going to say is I'm going to use the equation PE equals 1/2 kx squared. Now, I am going to use it twice for two different situations. So let's look at the first situation. The first situation, I have an energy, I have a displacement, (5 centimeters converted), and it allows me to solve for the K value. Now, since it's the same spring, once you solve for the K value is going to be the same in both situations. So, you can say PE equals 1/2 kx squared, so I forgot the K value, and you could solve for K. What I'm going to do is I'm going to do it algebraically. I'm going to say, well, I'm going to multiply both sides by 2 divided by x squared. And when I do that, I get 2PE over x squared equals K. Now remember, the K is going to be the same for both situations. So, if I were to somehow just say equals 2PE over x squared for the second situation, I've got a ratio. I don't even have to solve for K. So what I can do is I can say, okay, well, originally I had 10 joules of potential when I stretched it 0.05 centimeters. Or excuse me, 0.05 meters, which is 5 centimeters. Now, in the second situation, I want to know how much energy I have whenever I stretch it a total of 17 centimeters. Now, a lot of people will make the mistake here and they'll say, well, they'll plug in 12 there. But remember, this is stretching in an additional 12 centimeters. So it's stretched a total of 17 centimeters, which is 0.17. Well, at this point, you basically have one unknown variable. You can just cross multiply and you can solve. So what I'm going to do is I'm going to cross multiply, and I get 0.05 squared times 2, and so that is 0.005 PE equals 2 times 10 times 0.17 squared, 0.578. So now, divide both sides by 0.005, and what you get is, you get a potential energy of 115.6 joules. And so that just kind of puts it in perspective. Really, you're just about doubling, tripling the length, but your kinetic or your potential energy goes up quite dramatically. So you got to be aware of those sorts of things. So now, one other thing real quick, we went ahead and eliminated K. If you're not comfortable with what we did, you could always use the first situation to solve for K and then plug it in again a second time. We just showed you, we kind of skipped that step, but it's something that you could do if you're more comfortable doing that. A spring is 20 centimeters when 0 newtons is applied to it. What is the spring constant if 25 newtons stretches the spring to 28 centimeters? Now this is actually a review question, because if you look, it actually has nothing to do with energy whatsoever. What we're trying to do is we're trying to figure out what the K value is. And normally, so far, we've been saying, okay, PE equals 1/2 K x squared. And of course, we could do that. But really, there's another way of being able to solve this that works just as well, and that's this. We learned earlier this year about Hooke's law. Okay? And Hooke's law said that F equals K x. Okay? And we said that any sort of force that's applied will stretch a spring out depending on the value of the spring constant. So it says a spring is 20 centimeters when 0 newtons is applied to it. So now when it's 28 centimeters, we know that the x value is actually 8 centimeters. We know we don't deal with centimeters, so it would be 0.08 meters. We know that the force value is 25 newtons. And we can solve for it using Hooke's law. Hooke's law basically says 25 equals 0.08 K. Divide both sides by 0.08, and you get 312.5 newtons per meter. So now, we talked about the experimental origins of Hooke's law at the beginning of this when we talked about force. But you can actually get Hooke's law using conservation of energy. And I will leave that to you to see if you can figure out how to get this from some sort of variation of conservation of energy. So by now you should understand the factors that affect the elastic potential energy with an emphasis on displacement. So you should know that displacement number 1 has more of an effect on elastic potential energy than does the spring constant. And also you should realize that displacement is not just how long the spring is, but it's the change in the equilibrium position. You should also be able to calculate the elastic potential energy that results from some sort of spring and some sort of displacement, and you should be able to relate that potential energy from the elasticity to work, because you have to push or pull the spring, you have to apply a force for a certain amount of distance. You should also say, okay, well, the fact that the work done is equal to the elastic potential is indicative of the fact that energy is conserved.